Okay. So we're given the empirical formula and the molecular mass of the molar mass of our compound. And so we're trying to determine what is the molecular formula of the compound. So here the empirical formula is C2H5. So I want to determine the molar mass of the empirical formula. How would I go about doing that? Aubrey.
Yes.
How would I calculate the molar mass of the empirical formula?
So you would take the atomic mass for carbon and hydrogen.
Okay. So what is the atomic mass of carbon and hydrogen?
For hydrogen, it's 1. And then for carbon, it's 12.
Okay. How many hydrogens do I have?
5. So you times it
5 times 1.
is 5.
And then you said carbon. How many carbons do I have?
You have 2.
And the mass of carbon again?
12.
So 12 times 2?
24.
So we add them together?
Yeah. And it's 29.
Units grams per mole. Okay, so now I got the molar mass of my empirical formula. So I have the molar mass of my molecular compound, and then I have the molar mass of my empirical compound. So then I just divide them by each other. Diego,
Yes.
so tell me, what is 58 divided by 29?
Let me get my graphing calculator.
iPhone.
It's 2.
Okay.
Yes.
Okay, iPhone. I need your
I
help.
said yes.
I know, I heard you. I said I need your help.
Okay.
Don't take it personal. Relax. I haven't got
I'm not
wound up
Dr.
yet.
Henry. I would never.
Oh, okay, good. I'm glad. Okay, so if my empirical formula is C2H5, and based upon our integer here, that means that our molecular formula is going to be 2 times more than my empirical formula. So then what should be my molecular formula? If my integer between the two is 2.
What do you? It would just be doubled. So it'd be C4H10.
Now see how easy that is when we all work together and we talk to each other? Good job. So iPhone, who are you anyway? So I know who I'm talking to and I can give kudos to.
It's me, Giselle.
Giselle? Okay, Giselle. Thank you.
No problem.
Good job.
Thank
Okay,
you.
so as Giselle said, we just multiply our integer by the chemical formula, the empirical formula. And then that gives me my molecular formula. Piece of cake?
Yes.
Yeah.
Good, because this will be on the exam. And it'll be a little more intense than this. Just a little bit. Okay, so that brings us to a conclusion. Thank goodness, chapter 7 is done. Chapter 8, I have questions for you. Now, you guys have been doing chemistry since August, right? So in theory, you guys are budding young chemists, right, Whitney?
Right.
Excellent. So as budding young chemists, there are certain things that you should know at this point. So I have a really hard question for you, and I want you to think about it, and I want you guys to provide me some answers here, okay? So what are some ways, based upon all the things that you've seen and what we've talked about and what you've done, what are some ways that we can determine that a chemical reaction has occurred, or just provide me evidence of a chemical reaction?
Flame color.
You said sleep color?
Flame.
Flame
Like
color.
if we burn it.
So you're saying if something changes color?
Yeah.
Okay, so changing of color. Okay, cool. That's cool. I like that. Change of color. What else?
If chemical properties change,
What do you mean by that?
any like intrinsic chemical property,
What do you mean by that? Give me an
it
example.
could be like electronegativity.
Electronegativity.
It could
Okay.
be.
Yeah, that one is more of a physical property. If the electronegativity is being changed in some sense.
Okay.
Okay, so well,
Different elements combine to make compounds.
and what typically happens if that happens? What do you see? I mean, that's a great, you guys are like, don't get me wrong, Diego, you're on the right track there, right? But there's more. I want more. I want to know what happens. What do you see? What would be evidence? I mean, we know that that's what happens when a chemical reaction occurs, right? But what is it that you see? We saw, you said earlier, a chemical change, a color change, right? So we observe a color change. If it goes from green to hot pink, that usually probably means there's a chemical reaction involved in it.
Yeah.
Okay, so what else can you see that would be evidence? That would be proof.
Change in temperature.
Change in temperature, yeah. So if we touch something, it got really damn hot, that would be an example of a chemical reaction, right? Or it got really, really cold. We had two chemicals together and they got real cold, it froze up. Hey, that would be an example of a chemical reaction. Good job, Diego. What else?
Combustion.
Ooh, so that would be combustion. I like that one. So when I think about combustion, what do I get out of a combustion? What is combustion? I like that term. Tell me what
Two
it means.
things breaking apart.
Two things breaking apart. So yeah, I guess I could get two things breaking apart, but what does combustion really mean?
To combust.
What does that mean? So if your girlfriend or your boyfriend just come in and they're on flames, that's combustion, right?
Yeah.
Spontaneous combustion, right? So, okay. So what are you seeing in that case? You're getting heat, and what else are you getting?
Fire.
Fire,
Like
okay,
flames.
fire.
Yeah.
And what does fire also provide?
Warmth.
Okay, so we're back to heat again. Anything else that it can
Heat.
provide? In
Energy?
the old days, how did they used to read?
Oh, light.
Light. So if we get light emission as well. So
Okay.
if we got heat, light emission, and we have color change. Okay, so those are three. Can you give me something else? How many of you guys have gone in the refrigerator and you had some stuff in there that had been there for years? What is the first thing that you notice as soon as you open that refrigerator?
The smell.
Smell.
The smell, the odor.
Gas.
Oh,
Yeah.
Thank you. Yes, that's it. Gas formation. So that gives us 4. So we got gas formation. Now, also, if you go in the refrigerator and you look at your milk, right? And your milk has been sitting there for months, This happens to me a lot.
Ew.
And then you're like, God, I really want to have some cereal. I am craving cereal. And you don't pay attention. And you pour that milk, and then a big old clunk comes out.
Ooh.
So what is that an example of?
A mistake.
That
Uh,
would be true. But we're going from, because what milk is normally is it a solid, liquid,
liquid.
or
Oh, change of state.
change of state? Exactly. So if we get a change of state, like it becomes a
I
solid,
thought that was a physical change.
it's a physical change if there's no chemical change occurring with it. But if you go from a liquid, two liquids coming together and they make a solid, that's what happens. So in the case of the clumping of
okay.
milk, so you're basically, you have bacteria basically causing a chemical change occurring with that milk to cause it precipitation. And so that's why you get the milk clumping. Okay, so you guys did a good job there. Oh my gosh, it's like you guys want to participate today. Gosh, you guys are scaring me. I must have a fever. Is it hot in here or what? It must be a chemical change or something, right? So these are evidence of chemical changes, right? And so these are some of the things that we're wanting to pay attention to as we sit there and do our chemical reactions. Do you guys remember when you guys did the baking soda and the acetic acid, or the sodium bicarbonate and acetic acid? Did anybody do that experiment?
No.
Yes.
Yes, right? What happened?
It went boom.
Did it go
Coke was
boom?
launched up.
Did it really go boom?
Well, it sprayed.
Are you sure it's sprayed? Are we talking about the same reaction here? Didn't you?
A bunch
the
of
balloons-
Coke sprayed up. Or no, wait, never mind.
No, that was the Mentos experiment. We're talking
Wrong
about
one.
balloons.
It expanded. Balloon expanded.
Okay, because of what?
Gas expanded.
Because of gas expansion, right? So, and also if you actually touched it, the bottle got colder as well too. So you have two things that are going to
Yeah.
be going on in that case, okay? Okay, so let's get started on chapter 8. So chapter 8 deals with chemical reactions, right? And understanding chemical reactions and how to manage them and handle them. So one of the first things that we talked about was color change, right? So here's an example where we have a solution of sodium permanganate. As soon as we put sodium permanganate into a liquid solution, the sodium permanganate turns it purple. But over time, because the ion starts to dissociate, that purple color becomes clear, or less purple color. And that's because you have a compound that is together, and then you have water that's interacting with that compound, causing it to separate with each other. Here we have sodium nitrate and sodium chloride and silver nitrate coming together. And when they react, you form silver chloride, which actually becomes a solid and starts to precipitate out. So it forms a cloudy substance. And then over time, as we let it sit, it'll actually drop to the bottom to form a complete solid. Plop, plop, fizz, fizz, right? You throw Alka-Seltzer into water, what happens?
It becomes
It creates
gas.
carbonation. Yeah.
It produces carbonation. So we produce carbon dioxide from it, right? And how many of you guys like fireworks?
I do.
I do.
Me.
They're cool.
So fireworks are a perfect example of a chemical reaction, right? Because you get a double, a twofer. You get heat and you get light coming from it. And different color lights. So you get 3 color change, right? So depending on what the firework is made up of, it's going to either give you a green color or orange color. In this case, this guy would be sodium nitrate with aluminum, and it's packaged up and lit. So as soon as it lights, the nitrate gets oxidized, and then it causes the aluminum to cause the spark that you see the nice, beautiful color, and the sodium gives us the flame color it is. So if we wanted to change the flame color, we'd use a different metal. We use like barium if we wanted green. Okay, so glow sticks. How many of you guys have went to a rave and popped a glow stick? Light emission, right? How many of you guys run around the house and run into walls? Anybody? Come on, admit it. I know you've done it at some point.
On occasion.
On occasion, right? So your mom or dad or boyfriend or girlfriend had to pop open a cold pack to put on your head or somewhere on your body, right? So what happens when you pop a cold pack?
Crack it and it gets cold.
You crack it and it starts to get cold. So what happens in that case is that the energy or the heat from the surroundings, usually there's water on the outside, and then you have ammonium nitrate on the inside, and then when you crack it, it allows the water and the ammonium nitrate to interact with each other. And so the ammonium nitrate pulls in all of the energy to cause the reaction to occur, and so it gets cold. So it sucks in that heat, it absorbs it. So then you feel that cold effect. Okay, so let's talk about a chemical reaction. So here we have a piece of sodium. We're dropping it in liquid water. Now this liquid water has an indicator in it so that we get a nice color change to make it real fancy for you. So you guys can see the color change. You guys can see the color change, right?
Yeah.
Yes.
Okay, so when solid sodium is added to liquid water, a reaction occurs, producing hydrogen gas and sodium hydroxide solution and some heat. Okay, so can you give me the reactants? Do you guys remember what reactants were? I know it's been a while. What are your reactants?
The things you start with.
The things we start with, the things that we're going to be putting in the solution to react. Okay, so what are my reactants? Oh, let's
Water.
see. Water.
Water and solid sodium.
So what is the form of water? Solid, liquid, or gas?
Liquid.
Liquid.
Okay, so we're going to put a subscript liquid, right? And we know the chemical formula for water, even though I got ahead of myself and I was supposed to ask you, right? Now, what is the chemical formula for sodium?
Na.
Now, is this solid, liquid, or gas?
Solid.
So when a reaction occurs, we draw this arrow. Now you notice it's an arrow. It is not an equal sign. It is not a plus sign. It is an arrow. So we use that arrow to indicate that a reaction is occurring. And that reaction is going to be a one-direction reaction. You're going to make a product, okay? Or multiple products. So what are some of my products for this reaction?
Sodium hydroxide.
Okay, what is the chemical formula for sodium hydroxide?
Is it NaOH?
That is correct. So anytime that you see the term solution, that means it's dissolved in water or it's in water. So to imply that things are in water, we use the term aqueous, AQ. So what is my other product?
Hydrogen gas.
Hydrogen gas.
What is the chemical formula for hydrogen gas?
H and then the parentheses for gas.
H2.
Oh, somebody says H2. Why is it H2?
Because that's how it's found just in nature.
Because it's one of the 7
It's
diatomic
diatomic.
elements. That's right.
Okay, I forgot that part. Sorry.
Don't forget your diatomics. And then what else is another product?
Heat.
That's right. Okay, so for the remainder of this time, we're not going to worry about the heat. We're going to save that for another time to talk about. But for right now, we want to talk about the chemical equation. The very first thing that we did, we went through and determined the formula for each of our reactants and our product. And we made sure that each of those formulas were correct, right?
Yes.
Good. So the next part is that we want to make sure that we obey the laws of chemistry. The law of chemistry, one of the major laws of chemistry, is the law of conservation. What does the law of conservation say?
Mass cannot be created or destroyed,
Okay.
or energy
put it-
cannot.
Yeah, so to put it in layman's terms, what you put in, you must get out, right? So what are my elements that are going to be involved in this reaction?
Hydrogen, oxygen, and sodium.
So we have hydrogen, oxygen, and sodium. So on my reactant side, how many hydrogens do I have?
2.
2.
On my on my reactant side, how many oxygens do I have?
1.
1.
1.
And on my reactant side, how many sodiums do I have?
1.
1.
1.
On my product side, how many hydrogens do I have?
3.
3.
How many oxygens?
1.
And how many sodiums?
1.
Okay, so did we put in what we put in? Is that what we got out in the case of the hydrogen? We put in 2 and we have 3 out.
No.
No. So that means that this equation isn't balanced. So what we need to do now is try to find a way of balancing it without changing our chemical formula. Rule number 1, you never ever change the chemical formula. What we do is we put coefficients in front of that chemical formula. So we'll put coefficients in front of here and here and here and here if we need to, okay? So we want to play with our chemical equation to try to figure out what coefficients are gonna go in front of each of our reactants and our product, okay? So right now I have 2 hydrogens on my reactant side and 3 hydrogens on my product side. Is there something I can do to these guys to try to make them so that they'll be the same on both sides? Because we want to put what we put in, we want to get out. Is there a coefficient I could stick in front of these guys to try to make it so it's the same on both sides?
3 in front of the reactant side.
3 here?
Yeah.
Okay. So that would give me how many hydrogens?
6.
Okay, so I'll have 6 hydrogens and how many oxygens?
3.
Okay, so I have 6 hydrogens and 3 oxygens. So then what do I need to put on my product side?
For H2, I would just keep it as a 1.
Okay. And so
And
that would give me
then-
2 there.
Mhm.
And then how much would you put on your?
Oh, okay. So it'd be 2 sodium hydroxide and then 2 hydrogen gas,
Okay.
because that would give you 6. So then on the reactants, you'd also need a 2 in front of sodium.
Okay. Okay, so let's do that. Now let's look at oxygen. How many oxygens do I have now?
Oh,
2.
2.
2. So does that balance that out, even though everything else is balanced? So maybe we should
No.
start back from the drawing board, maybe a little bit. Let's take a step back. Oops. Of course. Erase everything that except for what I wanted to erase. So let's try something like maybe, what about if we put a 2 in front of the sodium hydroxide on the product side? If I put a 2 here, how many hydrogens would I have?
On what side?
On the product side?
Would it be
4.
4.
Okay,
Total.
4. How many oxygens would I have?
2.
And then how many sodiums?
2.
Okay, so what could I do to balance that out on my reactant side?
Put a 2 in front of the water in it and the sodium.
Okay, so then that would give me 4, 2, and 2. So is what I put in the same thing I got out?
Yes.
Yes.
Okay, so then that would be a balanced equation. Pretty simple.
Yes.
Yes.
I like it when nobody else answers, because that means that it probably isn't, but we're going to get you there, right? So sometimes it's a little bit of trial and error to kind of get us started, right? But I'll show you a couple of little hints to try to figure out which way to go. But you were right with starting with the hydrogen. It made sense because you have 1 hydrogen over here, and you have 2 that are located over here. Or we could have started with the oxygen but that was already at 1 and 1, and the sodium was already at 1 and 1. So it made sense to start off with the hydrogen. But we just started off a little too high. Okay, let's go. Okay, so again, when we're balancing the equations, we're going to be using coefficients. Coefficients are the numbers that are going to be in front of them. They tell me the quantity of that particular element or compound that we have in this chemical equation, okay? And they're essential. So nomenclature is the very first thing that we have to do. If we don't know our nomenclature, we're not able to write the chemical formula the way it's supposed to be, right? So that's why we are pushing nomenclature, nomenclature, nomenclature. So don't fight it, embrace it, love it. Okay, so your states are given to you in terms of symbols. So the S, parentheses S, subscript, parentheses S, solid, subscript, parentheses L, liquid, subscript, parentheses G, gas, and subscript AQ, aqueous, meaning it's dissolved in water. Okay, and so when you know it, you want to include that because you want to make sure that the person that is looking at this has the best and the most accurate information as possible. Do's and don'ts. Do's. You want to make sure that you have your chemical formula actually right? Before you get started, before you use any coefficients or anything like that, your chemical formulas have to be accurate. If they're wrong, everything is wrong. Okay. Don't ever change your chemical formula to try to make a a reaction balance. So you can't change the chemical formula once you're sure that it's right. Don't make stuff up. So don't add imaginary or real chemical species on either side of the equations just to try to make it balanced, right? So again, what you put in, you must get out. So you're not just putting things in randomly. They don't magically appear. So you want to make sure that you're not doing that, okay?
Okay.
Good so far?
Yes.
Okay. So the other thing is, the first thing that you want to do is write out your reactants. Draw your arrow, then write out your products. And be sure that they're correct. The next thing that you want to do is you want to sit there and add up the coefficients. Put in your coefficients to sit there and balance the chemical equation. Pretty simple, not too hard.
Pretty simple.
Okay, so let's test this out. Balance the equation for the reaction of solid phosphorus pentachloride with liquid water, yielding aqueous solutions of phosphoric acid and hydrochloric acid. Okay, Ariana.
Yes.
Help me out with these reactants. What are my reactants?
Solid phosphorus pentachloride.
Okay. Okay, what does that look like? What is the chemical formula for solid phosphorus pentachloride?
I'm not sure.
Take a guess. Phosphorus, solid phosphorus. What does phosphorus look like?
Phosphorus is just P.
Okay. And then penta means what? Like a pentagram or a
5.
5. And then chloride?
Isn't it? Well, Cl.
Cl. So that means how many pentachloride? I mean, how many chlorides do I have?
5.
See, wasn't that hard?
No.
That's going to cost you $500, right? Because you should know this, right?
Yes.
Okay, so I expect it on my next check, okay? So, one other thing, is it a solid, liquid, gas, or aqueous?
It's a solid.
So then what do I need to put next to it?
Subscript S in parentheses.
Okay, what is the other reactant?
Water.
Okay, what is the chemical formula for water?
H2O.
Is that a solid, liquid, gas, or aqueous?
Liquid.
Thank you. Good job. Let's see. Jacqueline. Jacqueline L. Where's my other? Oh, I have both of them here today.
Yeah.
So Jacqueline, help me out here. Phosphoric acid.
For this one, I always like to look at the ending. I know that it ends in ic, so I know that it comes from 8 because I
Okay.
ate organic apples. So it came from phosphate,
Okay.
which
So what
has
is,
a charge of -3, so we'll need 3 hydrogens, making it H3PO4.
okay. Solid, liquid, gas, or aqueous?
It's aqueous.
And hydrochloric acid?
That one is HCl, aqueous as well.
Good job. Jacqueline E.
Yeah.
Looking at it, is it balanced? Or first off, tell me the elements that we're working with.
Phosphorus, chlorine, hydrogen, oxygen, And I think that's it.
Okay, so is it balanced?
No.
No. So how many phosphorus do I have on the reactant side?
1,
How many chlorine do I have on the reactant side?
5,
How many hydrogens do I have on the reactant side?
2,
How many oxygens do I have on the reactant side?
1.
Let's see. Damaris,
Yes.
on my product side, how many phosphorus do I have?
1,
How many chlorines do I have?
1,
How many hydrogens do I have?
4,
How many oxygens do I have?
4.
Good job. Good job, by the way, Evelyn. I mean, Jacqueline. Sorry. Okay, so is it balanced? Erica, is it balanced?
No.
No. So what do we need to do to balance it? Where should we start? So right now we have one phosphorus. So that looks pretty good. That looks balanced to me. What about my chlorines? Do they look balanced? I have 5 on one side and 1 on the other.
No.
No, they don't look balanced. So how can I get 5 on the product side?
Can we just add a 5 to in front of the H?
In front of the HCl?
Yeah.
Okay. Let's do that. That sounds good to me. I won't argue. So then that tells me I have 5 chlorines. How many hydrogens do I have now?
No. 5.
5 plus
Oh, 5.
plus 3. I know my handwriting sucks.
Oh, 8.
8. Okay,
And-
so now I have 8 hydrogens.
So we add a 4 on the reactant side
Okay, in front of what?
in front of the H2.
H2O?
Yes.
In front of the water. Okay, so we have 4 in front of the water. So then that gives me how many hydrogens?
8.
And how many oxygens?
4.
Good job. Okay, is that balanced now?
Yes.
Yes.
Bam, that's it. Not too hard, right?
No.
Good job. Okay, so now we got a balanced equation. Okay. Are you guys feeling good now? I am. You're making me
Yeah.
feel so good today.
Yes.
Good job. Okay, so let's move forward. Okay, so now what does it really mean? So what does it mean when we're talking about these chemical equations, right? So we can talk about it at the particulate level meaning at the particle level, or as in a molecule, a atom, 2 atoms, 3 atoms, something like that. Okay, so when we talk about it at the particulate level, we're saying in the case of, did I go too far? Yeah, no, I did. So we're saying in the case of the formation of water from its elements, hydrogen gas and oxygen gas forms water, okay? So we have 2 molecules of hydrogen gas. We have 1 molecule of oxygen gas is going to make 2 molecules of water. Right? So literally, we're talking about adding 2 molecules of hydrogen gas reacting with 1 molecule of oxygen gas to make just 2 water. So that's at the particulate level. Now, when we talk about the molar level, well, we know a mole is a whole bunch of these, right? So you have tons and tons of it. So then we want to talk about it in terms of a mole, right? So 1 mole of hydrogen gas plus 1/2 a mole of oxygen gas is gonna make 1 mole of water. So in this case, we're looking at something that is macroscopic, large, huge quantities, okay? So we're able to sit there and do it for that particulate level and for that molecular level, or the, sorry, not molecular, molar level, okay? So you'll notice at the particulate level, we can't have 1/2 of a molecule, right? Because you can't have 1/2 of a water, right? Do you have 1/2 of a water molecule? Do I have 1/2 of an
No.
acinia?
No.
Azucena? No, I can't have 1/2 of Azucena, right? I have to take the whole thing, right? I have to take the whole Azucena, right?
Yes.
Okay. So that's the same thing at the particular level. You can't have 1/2, but at the molar level, we can have 1/2 because there's so many of them. You guys get that? So in the case, I have 2 Jacquelines, right? So I can have 1/2 of a Jacqueline, right? Because that's just 1 Jacqueline, since I have 2 of them. Okay, not a good joke, huh? Fine, nobody laughs. Okay, so this is just basically showing you that image, right? So we have 2 molecules of hydrogen gas, 1 molecule of oxygen gas is going to give me 2 waters. So when we talk about a dozen, right? And that's kind of scaling up. So I could have 2 dozens. 2 dozens of hydrogen gas, 1 dozen of oxygen gas is going to give me 2 dozens of water. Simple. Can you see it?
Can you repeat it again?
So if I have 2 dozen of hydrogen gas, 1 dozen of water, of oxygen gas, it's going to give me 2 dozen of water.
Okay.
Okay, so in that case, that's using the macro scale, right? So basically, we're scaling up, making a whole bunch of them. In this case, just 12. Okay, since it's a dozen.
Okay.
Okay, so now that you guys know how to balance a chemical equation, the next thing that we want to know is how to be able to identify the types of reactions that we're working with. So there are a couple of types of reactions that we're going to be talking about. And then we're going to go through them, and then I'm going to give you some special types. Okay, is that cool?
Yes.
Great. So the first reaction is called a combination reaction, or it's also called the synthesis reaction. So a combination reaction is where you take 2 different substances and you bring them together to form a single substance. Okay, so they're combined to make 1 substance. A plus X yields AX. Simple? Do you want an example?
Yes, please.
Okay, write the equation for a combination of aluminum and gaseous oxygen to form aluminum oxide. Okay, so what are my reactants?
Aluminum and oxide.
Okay,
Or
aluminum. Say that again, please.
Oh, I said aluminum and oxygen.
Aluminum and oxygen. What is the chemical formula for aluminum?
Al. And it's a solid, so we're going to put the S.
And you said the other one is oxygen?
Oxygen, yeah, but it's a diatomic, so it'll be O2.
Good job. Brownie points for remembering it's a diatomic. I'll get you those special brownies that you like. Okay. So what are we forming? Giselle. No, Melissa, you've been kind of quiet. Melissa?
Yes.
So what are we going to be making, Melissa?
I'm not sure if I'm right, but would it be aluminum oxide?
That is correct. It will be aluminum oxide. Good job. So now you have to tell me the chemical formula for aluminum oxide.
Okay. Would it be Al2O3?
That is correct. Good job. Is that going to be a solid, liquid, or gas?
It's gonna be a solid.
Good job. Okay, so now that we have our chemical formulas, now we get to balance it. So what are we going to do to balance it? Let's see. Whitney, you going to help me out with this?
Sure. You write down your aluminum and oxygen, and then on the reactant side, it's 1 aluminum and 2 oxygen.
Okay. Oops,
Uh,
I got carried away.
okay, yeah, that works.
That works? Okay.
Yeah. 2 and 3.
Okay. Okay.
Okay.
Is it balanced?
Mm-mm.
Okay, so what do we need to do to balance it?
So on the product side, I would put a 2 in front of the aluminum oxide, and then that would bring the aluminum to 4, oxygen to 6, and then put on the reactant side a 2 in front of aluminum and a 3 in front of oxygen. And then it's balanced because it's 4 and 6.
Okay. Beautiful. Simple.
Yep.
Good job.
Thanks.
Any questions? Am I going too fast? Did everybody get that down? Because I get trigger happy.
No, for this one, we have 4 aluminums on the products, right?
Let me go back. Let's see.
So why do we only have 2?
Ah,
did you
Oh,
accidentally
yeah.
put-
Okay, so 4 in front of aluminum.
good job.
For
Nice
some
catch.
reason, I thought the S was a 2. I don't know.
No, that was my fault. I overlooked it as well. So my bad. Good job. Good job, Jacqueline. Okay. Okay, so for our next reaction, it's called a decomposition reaction. A decomposition reaction is where you're breaking things down. So you have one product and you're breaking it down into 2 or more products. I mean, you have one reactant and you're breaking it down to 2 or more products. Okay, so we have AX and we're going to be making A and X. Okay. Let's see. Anissa, you mind helping me out with this one? The question says, water decomposes into elements when electrical energy is added. Write the equation. So what are my reactants, Anissa? I think Anissa stepped away from the, oops, oh, there's a message. Why is that working? Ah, okay, so water. Chemical formula for water?
H2O.
Solid, liquid, or gas?
Liquid.
Good job. Good job, Anissa and Diego. Diego is the translator. Okay, Diego, now it's your turn. So what are my products?
It's elements, so hydrogen and oxygen.
Okay, what do they look like? What are the formulas for hydrogen and oxygen?
H2 and O2.
Solid, liquid, or gases?
Gases.
Okay. Erica, is it balanced?
No.
No.
You need a 2
Okay.
in front of the oxygen on the product side. Or the, I forgot what side that is.
On which side?
On
product side?
the left
Left
side.
or right?
Left.
Okay. This side here?
Yes.
Okay. So in front of the water. Okay. Is it balanced now?
Oh, I'm confused.
Oh, let's see. How many hydrogens
You can't just
do we
put it
have?
in front of the O. You have to put it in front of the whole thing, huh?
That's right. You have to put it in front
Okay,
of the
because it's
whole
water.
thing.
Okay.
Yes. It's water, yes.
Yeah. Okay.
So then how many hydrogens do I have?
4.
Now on my reactant side. You said 4?
Yes.
Okay. And then how many oxygens?
2.
Okay. And then what about on my reactant side?
You need a 4 in front of the H2. I mean a 2 in front of the H2, sorry.
Okay. So then that would give me, good job.
Thanks.
See, you did pretty good. I thought you said you were confused. I wish I could confuse like that and get it, answer right. Good job. Okay, so certain reactions are going to be reversible. Reversible basically means that they can go either way, right? We can go in terms of decomposition, and we can also go in terms of synthesis. So the formation of water is a reversible reaction. It can also mean this double arrow going both directions, right? So it remains reversible, but it can also mean equilibrium, meaning that there's a point where both of the reactions are taking place at a given time, okay? And so that you'll have the hydrogen gas, the oxygen gas, and the water all in the same container, and it's going to be balancing each other out. And that's called equilibrium. Okay? Questions, concerns? Anybody want to give me cash? Okay.
Can you repeat the part of the equilibrium?
Equilibrium. So
Yeah.
equilibrium, so these double arrows,
Uh-huh.
so you guys can actually see stuff. So these double arrows basically means that this reaction can go, it's a reversible reaction, meaning that it can go both ways. So it's going in this direction and it's able to go in that direction. And this is a weird way of showing it. Normally you just write the equation once, going in both directions. That means that the arrow always points from the reactants to the products, typically. Equilibrium is kind of the same concept of both reactions existing, a reversible reaction, but they're going to be existing at the same point. And so these double arrows also are used to represent equilibrium.
Okay.
Okay. Clear. Okay, so our next reaction is called the single replacement reaction. So this reaction is where you're replacing one reactant for something in the compound. Okay, and usually this isn't based upon ions. So you're replacing an ion. So you're replacing a metal with one of the ions in that compound. Okay. And these are often redox reactions. So they're oxidation-reduction reactions. They're not always, but a lot of the times they're redox reactions. Okay. Oxidation means that you're losing of electrons. Reduction means that you're gaining of electrons. So you're gaining electrons. So, and we'll talk more about that a little bit later. But for right now, I like to think of this as replacing the old girlfriend for the new girlfriend, right? Because literally all you're doing is replacing one of the partners. Okay, so you're going from A plus BX to AX B. Okay. Now, usually this is done. So when you're doing a replacement, a metal is going to replace another metal, or a metal is going to replace hydrogen, or hydrogen is going to replace a metal. Okay. So hydrogen can kind of substitute for that metal, but none of the other nonmetals will. Okay. Hydrogen is kind of weird. Okay. Or you could have non-metal replacing another non-metal. But you're never going to get a non-metal replacing a metal. Did you guys get that?
Yes.
Okay, so let's test it out. Copper reacts with a solution of silver nitrate. Write the equation for the reaction. Azucena, gonna help me out?
So it's saying copper is it's gonna be
Okay. Solid, liquid, or gas, or aqueous?
it's
Let me give you a hint. All metals are going to be solids if they're listed by themselves, except for mercury.
solid.
Okay. And that's going to be reacting with?
With a solution of silver and nitrate.
So silver nitrate, with a solution of silver nitrate. Okay, so what does silver nitrate look like? What is the chemical formula for silver nitrate?
Ag, and it has a +1 charge. And nitrate has a -1 charge, so it's gonna be NO3.
Okay, so when I put them together, there won't be a charge on them at all, right?
No, because they're already balanced.
That's right. So we want to make sure not to put those charges there. Okay, so is it solid, liquid, gas, or aqueous?
That part I'm not sure.
So anytime that you see the term solution, you always want to put aqueous. So that basically means it's dissolved in water. Okay. So now I'm going to tell you guys a little something. So anytime that you're doing a single replacement reaction and you have a metal replacing another metal, almost all the metals except for aluminum, silver, and gold are going to have a 2+ charge if they're being replaced, if they're replacing it. So they're going to form a 2+. So in this case, copper is going to be 2+ when it reacts with the nitrate. Okay, so that's my hint for you guys. These guys, this guy's going to form a 1+. This guy's going to form a 3+. My bad, aluminum. Silver is going to form a 1+, and gold is also going to form a 3+. Okay, And that's only when they're doing the single replacement reactions, okay? Well, except for aluminum. Aluminum is always like that, and silver's +1 almost all the time. Almost all the time. Okay. So what are going to be my products if I'm replacing the old girlfriend for the new girlfriend?
So it's gonna be copper. And then NO3. But copper has a 2+ charge, so it's gonna NO3. You're gonna need 2 of those.
Okay, good job. Okay, and these are going to be an aqueous solution now. And then what is going to be left over?
The AG.
Okay. Is that solid, liquid, or gas? It's a metal.
Solid.
That's correct. Yep. Okay. So is that balanced? Giselle, is it balanced?
No.
Okay, so what do I need to do? What do I need to do to balance it?
Well, first I would identify all of the elements, like the numbers that you did, how you would like.
So we have AG. So I'm going to use a little cheating method here. So you see we have NO3 here, right? You guys see that?
Mm-hmm.
And then we have NO3 here, right? You see that?
Yeah, but then because if it's in parentheses, would you have to multiply it?
Yeah, so there would be 2 of these, right? 2 of those, and there's 1 of these over here, right? So because they're moving as a unit, the polyatomic ion is able to move as a unit. In other words, it's not being broken down and mixed between the two. We can actually just use it as if it's 1 unit, okay? And so all we have to do is try to balance out the polyatomic ion to make our lives a little bit easier. But you don't have to. You can do them separately if you want to, because it works out that way too. Do you want to try it out this way and see how it comes out? Or do you want to do them separately?
Doesn't matter.
Okay. Okay, so tell me, how many silvers do I have on my reactant side?
1,
And on my product side?
5.
Silver?
Oh, 1, sorry.
Yeah, that's an S.
Oh,
Sorry.
okay.
Sorry about the horrible handwriting. That's an S. So that's 1. Okay, copper? That's an S too.
1.
And on my product side?
1 as well.
Okay. So what do I need to do to balance out those nitrates?
Double the NO3.
Okay, so how would I double my NO3?
Double silver nitrate.
So I put a 2 in front of the silver nitrate.
Yes.
So then that would give me 2. And then now my silver has 2. So what do I have to do to the other side? Giselle?
I would add a 2 to the AG.
Okay.
And I would just leave it like that.
Okay, that's it. Everything's balanced. 2, 2, 2, 2, 1, 1. Piece of cake? strawberry cake with chocolate frosting and slices of strawberry in between? Good. Okay, so my next reaction is called a double replacement reaction. So, or a double displacement reaction. So in this case, all you're doing is changing partners, right? So it's two ionic compounds and you're changing partners. So your cation is going with that other anion and vice versa, okay? So I also like to call this the swinger reactions. Do you guys know what swingers are? Melissa, do you know what a swinger is?
No.
No. Anissa, do you know what a swinger is? Ariana, do you know what a swinger is?
No.
It's a person who goes around and sleeps with everybody.
Not everyone, that's a polygamist.
Oh,
So that's a little different. A swinger is you have two
Is-
couples and they exchange partners, right? That's what a swinger is. So here you have two couples. You have AX, BY. A is going to hook up with Y and X is going to hook up with B. Okay, so you're just changing partners. So this is a double replacement reaction, or like I like to say, a swingers reaction. Okay, you want to test it out? Oh, before we go there, so you'll see the term or precipitation or precipitate, right? Anytime you see that term, that basically means that a solid is going to be formed when you mix two solutions. So one of your products is going to end up producing a solid, okay? Are you with me?
Yes.
Okay. I always forget that your audio is not working, Anissa. And so I'm like, I'm talking to her and she's just ignoring me. Okay, so here we have silver chloride precipitates when the solution of sodium chloride and silver nitrate are combined. Write the equation for the reaction. Okay, Whitney, what are my reactants?
sodium chloride and silver nitrate.
Okay, sodium chloride and silver nitrate. Excellent. Okay, so what are the chemical formulas for sodium chloride?
It's just NaCl.
That's right.
And then silver
it's
nitrate. Let me check the ion thing. 1 second.
okay.
Oh, where is it? Okay. Nitrate. Oh, it would be silver and then just NO2.
Okay, what is silver?
Ag.
Ag. Okay. And you said NO3.
3.
NO3. Okay. Okay, is it solid, liquid, gas, or aqueous?
So aqueous.
Okay.
Both of them. Yeah.
Okay. Okay, Diego.
Hi.
So what are my products?
It precipitates. Honestly, I do not know.
So read
My
the question.
mind went blank right now.
Okay, so if we're doing a double replacement reaction, so we're mixing partners up. So sodium is going to partner with who?
Nitrate.
Okay, yep, so we're going to get sodium nitrate, so that's going to be one of them. So what is that going to look like?
NaNO3.
So I'm just going to give you this so that you guys know. Anytime that you have something paired up with nitrate and it starts in an aqueous solution, it's going to end up in an aqueous solution. So it'll never form a precipitation. Okay, okay, Diego. So then what must be my other product?
Aluminum chloride.
I don't see aluminum here.
Not aluminum, silver.
Okay,
Silver chloride.
okay, so what is the chemical formula for silver chloride?
AgCl.
And we know that from their problem, it says silver chloride precipitates. So what does that mean?
That it's not aqueous.
Okay, so if it's not aqueous, then what is it? What does precipitate or precipitation or precipitant mean?
Didn't you say it becomes a solid?
That is correct. It becomes a solid. So we're going to put an S there. Okay, is the equation balanced?
Yes.
Okay, it is. That's it, piece of cake. Good.
Sure.
Okay, so a special case for a double replacement reaction is the neutralization reaction. The neutralization reaction is just when you use an acid and a base. Both of those are ionic compounds or ionic solutions, okay? So they're also going to do a double replacement. So anytime that you have an acid and a base acting together, an acid is always going to have that H plus ion, and the base is going to have the OH ion. So anytime that you have an acid and a base reacting, you're going to get water because they're going to come together. And then you're going to get a salt, which is going to be a metal and a non-metal. So do you want to give it an example? Do you want to try an example?
Yes.
Okay. Write the equation for the reaction between sulfuric acid and sodium aluminum hydroxide. Okay, so we'll make this open because I know you guys are all excited. So, what is the reactants?
Sulfuric acid.
Okay, sulfuric acid. What does sulfuric acid look like? What is the chemical formula?
H2SO4.
Solid, liquid, gas, or aqueous?
Aqueous.
I think it,
That's right, aqueous. And what else is the reactant? What is the other reactant?
aluminum hydroxide.
Okay, what does aluminum hydroxide look like?
AL,
Yeah. AL
parentheses,
and OH in parentheses and subscript 3.
Okay, what are we going to make? Oh, is it solid, liquid, or gas?
Solid.
Okay, so what are our products?
Water and
Is
aluminum
H.
sulfate.
So water. And you said aluminum sulfate. What does aluminum sulfate look like?
AlSO4.
Is it completely balanced?
Let me check my
No.
table.
Okay, how do I completely balance it?
You need 2 aluminum.
I need 2 aluminum. And then how many sulfates?
1.
Are you sure? Because it isn't aluminum plus 3.
Oh, okay. 3.
Okay. And that's AQ. Okay, is it balanced?
No.
Okay, what do I need to do to balance it?
Write out all your elements.
Okay. Okay, on my reactant side, how many aluminums do I have?
1.
Oxygens,
7.
hydrogens,
5. 1.
sulfur. Okay, product side,
2.
oxygens,
13.
hydrogens,
2.
2.
sulfur.
3.
Okay, is it balanced?
No.
Okay, so what do I need to do to balance it?
Multiply some things on the.
You
Uh,
said
on the
multiply
real-
some things. Let's start with the aluminum.
Double it.
What was that?
You have to double it.
So I need to do what? What does that mean?
Double the amount of aluminum hydroxide.
So what does that mean?
Change it
Where-
from 1 to 2 aluminums. Put a 2 in front of it.
Okay. So that gives me 2 aluminums. How many oxygens do I have now?
Uh, 10.
How many hydrogens?
8. No, wait.
Okay.
No, wait. It'd be 7.
Are you sure?
Hold on.
Right now there's 3 times 2, that's 6, plus 2,
6.
that's 8.
8. Yeah.
Okay. So is that balanced?
No.
Okay. Let's see. So what do I need to do to balance? How many sulfurs do I have? How can I make that so there's
You're gonna need to make 3 sulfuric acids.
okay? So how many sulfurs is that now?
3.
How many hydrogens?
It's gonna be 12.
Okay. How many oxygens?
Oh wait. $13.
Are you sure? 3 times 4 and 2 times 6. I mean 2 times 3. What is 3 times 4? Is that 12? 3 times 4 plus 6.
That's 18.
Okay. Okay, is that balanced?
No.
Okay. So what do I need to do? How many hydrogens do I have over here? Currently?
2.
Okay, so if I wanna balance it out, what do I need to do?
Multiply it by 6.
Okay. So then that would give me how many hydrogens?
12.
Okay, let's count my oxygens. I have 6 plus 3 times 4.
6 plus 12, 18.
Okay, are we balanced?
Dr. Henry, I don't know
Yes.
if you have another class, but it's 9:38.
I know, I do.
Okay. All right. All right.
Yep. I'm running a little late. It's okay. So, piece of cake?
All right.
Okay. So, good job, Diego. Okay. So, this is the last slide. It's just a summary of all of the reactions that we talked about. We have one more reaction to talk about, and that's the combustion reaction. And we'll be talking about that next week. Do you guys have any questions?
Nope.
Nope. Then I will see you guys next week.